Welcome to Lesson 3 from Learning Unit 3. The title of the lesson is Joining and Other Integration Technologies for Production of 2D and 3D Smart Textiles. This lesson is part of the MOOC on Advanced Textiles Manufacturing Industry developed by the Hacktex project. The lesson is prepared by Dr. Mohammed Niyaz Morsid from the University of Borås in Sweden. In this lesson of Joining and Other Integration Technologies for Production of 2D and 3D Smart Textiles, we will discuss briefly about the joining techniques of smart textiles, different connection approaches as well as common fabrication methods. Content. The content of the lesson has been divided into two parts and a summary at the end. The first part will discuss the overview of joining techniques of smart textiles. The second part will discuss the common smart textiles fabrication methods. Let's start with overview of joining techniques of smart textiles. Joining and integration techniques play a crucial role in the development of smart textiles. These techniques enable the seamless integration of electronic components into fabrics, ensuring functionality, durability, and user comfort. Joining and integration techniques for development of smart textiles includes, but are not limited to, physical, mechanical, and chemical approaches. Joining techniques must satisfy being flexible, lightweight, breathable, stretchable, and washable to offer a superior usability, comfortability, and non-intrusiveness of the resultant smart textile. The joining and integration of smart textiles have been divided into two categories, the first one being attachable joining technologies. Attachable joining technologies are typically electromechanical components such as snap fasteners or USB connectors, used for functions such as attaching a power source to an e-textile garment. And the second one is fixed joining technologies such as stitching or soldering, used for example to attach electronic components to flexible substrates. These joining and integration techniques not only enable the incorporation of sensors, actuators, and connectivity modules but also ensure the flexibility, washability, and stretchability of smart textiles. The continuous advancement of joining and integration techniques paves the way for the creation of smart textiles with enhanced functionality and seamless integration into everyday garments and applications. Let's have a look at the common smart textiles fabrication methods. Smart textiles can be fabricated in a number of ways. First of all, smart textile can be fabricated using textile fibers that have additional functions, for example electrical or optical conductivity. Secondly, through attachment of commercial off-the-shelf components such as integrated circuits or light-emitting diodes to the textile after fabrication, and finally through hybrid approaches combining both commercial and textile functionalities. As mentioned earlier, these joining and integration be either fixed or attachable. There are several joining and integration methods used in the development of smart textiles. These methods enable the seamless integration of electronic components, sensors, and connectivity modules into textile substrates. Each joining and integration method offers different advantages and is chosen based on the specific requirements of the smart textile application. By employing these techniques, electronic components can be seamlessly integrated into textiles, enabling the creation of functional and interactive smart textiles. Some of the methods for smart textile joining and integration are mechanical connectors, soldering, sewing and embroidering, hybrid solder and sewing integration, electrical conductive adhesive, inkjet and 2D screen printing, 3D printing, stretchable electronics as well as e-threads. Joining and integration methods based on technology perspective. Here you will learn about the joining and integration methods from a technological perspective. Based on that, the methods can be divided into technology groups such as surface technology, hybrid and embedding, fiber and yarn. Printing and laminating is the examples surface technology. Embroidery is an examples of hybrid and embedding. Weaving and knitting is the examples for fiber and yarn technology group for joining and integration methods. On the following slides, there will be brief description of some of the common methods. Mechanical connector. Mechanical connectors are another approach used for joining and integrating electronic components in smart textiles. Mechanical connectors provide a reliable and removable connection between components and textile substrates, allowing for flexibility and interchangeability. As you can see on the images on the slide, mechanical connectors are physical attachments of textile fibers that have additional functions, or integrated circuits or light-emitting diodes to the textile after fabrication and wire with the textile by using different methods. Example of mechanical connectors includes snap buttons, socket buttons, bolt connection, ribbon cable connector, etc. Snap button consist of two separate pieces, typically made of metal or plastic, that snap together to create a secure connection. They can be easily attached or detached, allowing for the replacement or repositioning of electronic components as needed. Socket buttons consist of two separate components, a male part and a female part. The male part typically features a central post with a protruding knob or button, while the female part consists of a socket or ring with an opening that matches the shape of the button. Bolt connections involves the use of bolts or screws that pass through components and textile substrates, securing them together through threading. A ribbon cable connector consists of multiple parallel conductive wires or traces arranged side by side in a flat, ribbon-like form. Soldering. Soldering creates interconnections between conductive textile material and microelectronics by melting a filler metal or solder and putting it into the joint. Soldering also enables precise and intricate connections, as the molten solder can flow and fill small gaps or spaces between components. This capability is particularly useful for soldering surface mount components, which have fine leads or pads on their surfaces. This method allows mounting of electronic components directly onto the textile surface. Soldering process transfers heat either by conduction, convection, or radiation. Solders are generally soft alloys of lead, tin, or silver, etc. There are several types of soldering, among them, frictional soldering, hot air or thermal soldering, ultrasonic soldering, laser soldering, and infrared soldering are the name of few. Sewing and embroidering. Sewing and embroidering are traditional textile techniques that are also employed in the context of smart textiles for joining and integrating electronic components. These methods involve the use of needles, threads, and decorative stitches to create connections and incorporate electronic elements into fabric-based structures. Sewing and embroidering offer several advantages in the development of smart textiles. They provide a reliable and durable connection, ensuring that electronic components remain securely attached to the fabric. These techniques allow for flexibility and customization, enabling the creation of complex textile structures with integrated electronics. Recently, the advanced embroidery machines to integrate electronics into the textile substrate has been introduced. For this method, often special yarn and needles must be used, which allow embroidering without yarn breakage, which results in high-resolution circuit and high resistance to washing cycles for the smart textiles. Another method for the fabrication of smart textiles is inkjet and 2D screen printing. In this method, the fabrication of smart textiles is performed by primary printing techniques, such as screen printing or inkjet printing, where the printer prints functional materials on a textile surface. Through this method, electroactive functional inks are used to develop textile-based functional electronic devices. The smart textiles that have been designed through inkjet or another 2D printing method, the resultant textiles often tend to be rigid and inflexible, which offer limited skin compatibility and are damaged under washing. Nevertheless, smart textiles produced through inkjet and 2D screen printing methods can be uncomfortable and less breathable. Another method for fabrication of smart textiles is three-dimensional or 3D printing. In this method, functional materials are captured on a computer-aided design model and then subsequently fabricated in a layer-by-layer manner on textiles. This method works with the principle of the fused deposition method technology. The smart textiles from this method are sensitive to mechanical abrasion. This method can offer the integration of functional materials on textiles with high precision, performance and connections while offering the printability of multiple layers. Weaving is a traditional textile technique that involves interlacing yarns or threads to create a fabric. In the context of smart textiles, weaving can be utilized to integrate electronic components, sensors, and conductive materials directly into the fabric structure, resulting in functional and interactive textile systems. The weaving technique can generate large area textile surface both in 2D and 3D weaving. Weaving techniques can be used to develop uncut garment. Smart textile developed through weaving methods are often durable and maintains better resistance to washing cycles. Last but not least, the knitting technique is also one of the most common technique for joining and integration of 2D and 3D smart textiles. Knitting is a textile technique that involves interlocking loops of yarn to create a fabric structure. In the context of smart textiles, knitting can be utilized to integrate electronic components, conductive materials, and sensors directly into the fabric, resulting in functional and interactive textile systems. Just like weaving, the method produces durable smart textiles that can withstand high washing cycles. Modern machines are capable of knitting complex 2D and 3D structures to develop 2D and 3D smart textiles. Here we come to the end of this lesson. This lesson summary includes following conclusions. First of all, choice of joining and integration techniques for development of 2D and 3D smart textiles depends on the application of the end product. Over the years, several joining and integration techniques has been introduced from basic weaving, knitting, coating, sewing to three-dimensional printing. Joining techniques often influence the performance of smart textiles in terms of durability, comfort and accuracy of the functions. Finally, integration of functional materials into textile for the development of smart textiles shall be done without affecting or influencing the final design and characteristics of the textile substrate. Thank you.